Okay, now that we have the gravity load analysis completed for the beams and the columns, we'll move into the lateral frame analysis for the bracing members, beams and columns. So we invoke ram frame by clicking on that icon. And the first thing that we do always whenever entering a new module is, of course, to set the criteria for design. So go to the criteria menu and then go to general. And here we have the general criteria dialog box that is providing us with various parameters, if you will, various pieces of design information that is applicable to lateral frame analysis and design. You can get into the details of each one of these sections by clicking on the help menu and reading further into each one of these settings. Just a quick overview. Rigid end zones. When you ignore the effects of rigid end zones, essentially what you're doing is allowing deformation to occur within the beam column joint. It's oftentimes your worst case scenario. When you include it, of course, you would then need to be able to determine the reduction percentage that should be applied to your beam column joint. Typically ignore these at this point for most of my analysis unless there's a compelling reason to include that information. Member force output, self-explanatory, at the face of the joint or at the center line of the joint. Typically use it at the face of the joint. For response spectral analysis, that doesn't apply to what we're doing, but if you're a structural engineer, you can read into what response spectral analysis is about. It's mainly for dynamic analysis, earthquake in particular. Eigenvalue analysis, well, this deals with calculating the buckling load factor, so to speak, and which method that you're going to use to calculate it. These three methods are available. Eigenvector, subspace iteration is what is the default, and I typically use the default. Of course, diaphragm forces that can be stored or not stored based on the user choice. P delta, whether you include it in the analysis and then lateral analysis or if not, you have the choice. And when you do include it, you then have two more choices to make at the very least in terms of what is the mass load factor, scale factor, or gravity load is what I typically use. And then I scale up my loads based on the load combinations that are applicable for the lateral load case that I believe to be controlling my lateral frame design. And here, these load factors are for RAM frame. Uh, they are values that are at the ultimate load level, and it's really somewhat design methodology dependent. However, these values are typically used as the LRFD method load factors, even though the engineer may be designing the structure using ASD methodology. So these load factors for the lateral load case that we're concerned with, earthquake and wind, the worst case scenario would be 1.2 for dead. If I could get it done. Live load can be factored or not factored. 0.5 for roof and 0.5 for snow. As you know, Snow and roof loads are not applied simultaneously, but interchangeably. You might ask where are these factors coming from exactly? Well, they're coming from the building code. In my case, that's the IBC, and they're also pegged to ASCE 710. And in section 2.3 of ASC 710, we have the load factors that are provided for us. And then wind load combinations, this is the 1.2 factor dead load, the 1 on the live load, the zero point 0.5 on the roof load or snow load or rain load, as may be the case, in combination with an unfactored, if you will, wind load because it's at strength level. Of course, when you have earthquake, we have the same thing as far as the load cases, with the exception of for snow loads, it can be taken down to 0.7, and you can also just use 0.5 for roof load if that so happened to be the case. So this is the load factor that I typically, this is load combination rather, that I focus on oftentimes as far as the worst case scenario. This other load factor 3, it involves using wind, but you'll be reducing the wind load by a half and increasing your load factor for the live load by 60% here using 1.6. That's not likely to be the controlling load case. So where these values are coming into play mathematically is that your stiffness matrix, your geometric stiffness matrix in particular, will be modified by these load factors. So whatever axial load that is in the structure based on that load case, it will be increase or decrease based on these load factors, and then added together individually using the principle of superposition essentially. Now this P delta analysis and these load factors will be used for each case. RAM frame actually happens to use a different method than an iterative method to determine the P delta analysis, P large delta and P small delta. And so they use something called the geometric stiffness method. And in that method, the typical elastic stiffness matrix that we are used to is modified by a geometric stiffness matrix. All right. That this is the geometric stiffness matrix that RAM frame uses, as far as I could understand. And this F sub x2 is the axial load that is used. Now like I said, the value that we use is a combined load value. And so the dead load will be multiplied by 1.2, live load will be multiplied by 1.0, roof load by 0.5. All those loads will be added up together and then included in the stiffness matrix analysis. This would then reduce the elastic stiffness of that structure and cause it to be essentially weaker than it would normally be for the case of for lateral load cases. Okay, so this is an example, even though this is not exactly what RAM is doing, but this is an example of combining stiffness matrix. You could just ignore the case of M right now because it's an elastic analysis, and M is dealing with plastic or inelasticity behavior. So case of E and case of G is added together, and that is multiplied by delta to end up with a force matrix, internal forces, so external force matrix. But either way, you end up with the force matrix, and the the axial load have a destabilizing effect or reducing effect on K sub E, and that's taken into account, like I said, um, by the direction of the sign of the axial load, and compression will cause it to reduce. Tension would actually cause it to increase the stiffness, the lateral stiffness. All right. So that's the long and short of it. This is the three-dimensional version of the K sub E value. I mean K sub G value. All right. There's a discussion on RAM structural system, I guess, website, and they talk about it more into details, but they use a geometric stiffness matrix analysis or method so that the analyses can run faster on the computer. They do not analyze lateral load and vertical loads in combination and take a look at the effects of that structure as the structure deforms under both cases. Instead, it's an individual load case. That's the key factor here. It's individual load cases. So it's a linear, first order linear elastic analysis, essentially, that's being applied and modified a little bit with the stiffness matrix, modified a lot with the stiffness matrix. And then those individual load cases are subsequently combined using the principle of superposition. And that's why these load factors correspond to the ultimate strength level versus using 1.6 ASD and then taking the results of that analysis and dividing it by 1.6 in order to design forces for it. So we go into this in further detail, but the gist of it is that these load factors correspond to LRFD load factors, even though you're using the ASD method. All right. And this is not an iterative analysis. So it's not a so-called rigorous structural analysis, rigorous second order elastic or second order inelastic. It's an approximation. All right. So it's an approximate method. All right. The other things, the solver type, you can see this is all boxed in overall. So that solver type, these are the different solvers that are available. There's not a need to modify any of these defaults right here. So we leave it for this analysis, for this type of structure. Okay, so obviously this is the option to select the use of the direct analysis method. In this case, we will. And to find out what the tau beta value is, if you wanted to use a different value of tau beta, if you knew what it was already, you can do that. But this is a iterative approach in order to determine what tau beta is, tau sub b is, if you will. You first have to run the analysis and then look at the performance of the structure, go into each individual member, and it will give you various tau sub b's. And they may, RAM may actually have a table, a report that provides you with the various values of tau sub b's that are found for each one of your compression members. And then you use the worst case scenario for the entire structure. Or if you design your structure to be relatively stiff enough or the load is not that high, tau sub b can be equal to 1.0. Again, this information is found in Chapter C of AIC 360-10. All right. The wall element, if you have wall elements, these are settings related to wall element. We don't have any in this model right now, so there's no need to go into that in detail. Buckling restraint braces, again, this is not in our model. excluding it or including it doesn't make a difference because it's not in the model. Um, so the analytical model itself, merge node tolerances, leave the default as it is. What is the maximum distance between nodes on the mesh line? 4 is can work very well. I start off with 4, but then I tend to take it down to a smaller number once I have my structure working properly to get what I believe to be a little bit more accurate information. So we'll start off with 4 for now, and then we'll change it later. Geometry tolerance. You can read the help about what geometry tolerance is, but it's in value. That basically deals with, my understanding is that it deals with convergence. All right, but that information is found in the RAM frame manual, and you can go into that in greater detail. Here, this particular area is not talking about it. Oh, here it is. The geometry tolerance is mostly used in geometry calculations as a threshold tolerance. This should not be confused with a merge or a close node tolerance, which is explained below. All right. And then it gives an example. Examples are as follows. It is used as a tolerance to check a node is on a line or to check a point is within or inside of a polygon, etc. So it's a geometric tolerance. So okay. The key thing in all of this in this dialog box, if you don't do anything, you don't get anything right, or you don't modify anything. The one thing you need to modify is to include P delta for your direct analysis method, and to use the gravity load factors that correspond to LRFD design, um, and then you can decide whether or not you want to include tau beta, which generally start off with tau beta equal tau sub b rather equal to 1.0. Right? So okay. Now getting into this diaphragm, you can have a rigid diaphragm, flexible diaphragm, pseudo flexible diaphragm, or semi rigid diaphragm. You can get into this help menu, and it describes all these settings, the diaphragm settings. The two that I typically use is either going to be rigid or semi-rigid. Sometimes I find a need to use pseudo. Uh, there's a discussion on RAM website, Bentley's website. I can tell you about what happens to the structure for each one of these different settings, or what's the intent, all right? So the most accurate actually is to use semi-rigid and to give the diaphragm properties. And we had provided those properties when we used RAM Modeler. Uh, and that was our non-composite deck that we defined, and we gave it some values for the thickness, Poisson's ratio, and Young's modulus. Those values all are used when this semi-rigid diaphragm setting is selected. And this is actually something that you need to pay attention to, because when it's semi-rigid, it behaves, the values that you use in RAM Modeler for your Young's modulus actually will affect your structure. It will affect the results of your structure and the analysis, and whether you get warnings and things of that nature. And I'll show you that in a minute. But here, because we have a one-way deck, all right, so this is whether or not you include the outer plane stiffness. For now, I'm not going to include anything, all right? I will show you the effects of including it or excluding it based on the properties that are set for semi-rigid, all right? Actually, I'll just include it. So second case, I'll include it for now, and I'll show you the effects, what happens when you exclude it and you vary these properties for your semi-rigid diaphragm, all right? So gravity member supporting two-way decks. I don't have that case, but obviously there's a settings related to it. You can read into it on your own and figure out what it is. The diaphragm mesh, well, that's the same distance that, as far as the distance between those, it's going to be the exact same factor that we've seen in our previous dialog box. So you watch, if I change this from 4 to 2 in this dialog box, say OK, RAM automatically picks up down on that and changes this mesh control distance to 2. So I could change this back to 3, just so you know. I'm not trying to fool you. Come back and get into diaphragm, and voila, this is 3. All right, so that value varies. Like I said, I'll use 4 for now. Everything else is self-explanatory. Diaphragm boundary, whether you use the slab edges or the beams on the perimeter, is the user's choice. Typically, I use the slab edges. Diaphragm mass, use the calculated mass or uniformly distribute total mass over the diaphragm. Use the calculated mass for now. Then it has a note right here that tells you that semi-rigid diaphragms are always meshed, and rigid diaphragms are also meshed if they contain any two-way decks. All right, so that's just a little piece of information you should be aware of. So, okay, uh, ground level settings at the base. You can modify that if you had a multi-level structure and you wanted the ground level to be at the first story or something like that, because you have a basement level. So, okay. Redundancy factors. This is related to the earthquake analysis. Here, let's just make sure we set our code. If we were to use redundancy factors, we set our code to IBC value, code values, not the UBC. And here it's asking you, obviously, if your system is dual or not. And then the other things that you can use, these other parameters are related to earthquake. You get into the analysis, get into the discussion of earthquake requirements in ASCE 7, and also through this help menu, and provide values for these settings accordingly. Reduced beam sections, we don't have any. Buckling restraint, we don't have any. Buckling restraint braces, side plates, not applicable for what we're doing. And RAM also allows you to provide an analysis based on stages of construction. We're not going to deal with that right now, because what we're concerned with is the behavior of the building after everything has been constructed and it's in its final state. And that's what we're interested in here. So let's see here. Okay. Let's reset the structure real quick. All right. So I save my settings. The next thing is, of course, you have your modes, and you're in analysis mode or a design mode. The design mode would be the still mode right here. In the analysis mode, you could be looking at load cases or load combinations. In the still modes, you could be looking at your standard provisions or your seismic provisions, depending on the type of structure it is, your R factors, etc. Drift control, and you have to enter another mode to see the shear wall forces and deal with their load cases or load combinations accordingly. So nothing special here. Assign, we'll get into that as we work through the example. But the assign menu is similar to what we've seen in Modeler. So loads, gravity loads. When you click on this dialog box, you can have a view of your gravity loads that the diaphragm has collected, or the structure. You can use the calculated values, or you can specify values. Again, help menu is there to guide you. Use calculated values will be used in this analysis by default. when you when there is sometimes there are loads that the computer has calculated but not assigned it to a diaphragm. You would then use a drop down menu right here to assign that load to a particular diaphragm. So okay. Uh, again, you need to use your help menu to understand this. Uh, but these diaphragm loads, okay, diaphragm gravity loads are used for notional load cases and for P delta loads. So that's very important. So okay, masses. Again, this is dead weight, and you can use the specified values or user values. Right now, it's calculated the weight of my structure as 283.39 kips, and this is the mass. This is the for this diaphragm. This is where the center of mass is. These are the eccentricities that are associated with that center of mass in this diaphragm. According to these calculations, you should do hand checks to verify this information. I've done it in the past, and it's very accurate. However, as you get into the details of modeling structures in the real world, you want to do your best to validate that accuracy as much as possible. All right. So you still have to pay attention to this, but in general, you can trust RAM that this is right for most structures. And you might want to, if you have a really unusual diaphragm situation, you want to get into the details of these values and ensure that you can back check it with your hand calculation or another computer for that matter. All right, so you should be aware of what's going on here. Then the exposure, this is for your building exposure. This is basically your building envelope, your wind cell, if you will. So the amount of area that's subjected to wind. If you have a parapet on the structure, this is the place where you would define that parapet height. This will definitely affect your wind load analysis. When you get into ASC 710 and you look at the values that they have for the parapet, you will see that the higher your parapet is in terms of height from the roof, the larger your wind force will be. This has a dramatic effect on the wind force. So be aware of your parapet height and include it when necessary. And I'll say if you have at least I would say if you have at least a 2 foot parapet, you might want to include it. 3 feet, anything greater than 2 feet, you want to include it. 2 feet is not really going to have a dramatic effect, but that's when I'll say you start to include it. Not a tiny little curve that's 6 inches or a foot or something like that. It may not be necessary. Um, so again, full exposure or non-exposure, this will be set by the user in order to figure out what exposure is applicable for this diaphragm number. All right, full exposure is what we're going to use for this example. It's what is typically used in all situations, but you want to verify that because if it's a basement level, it's not exposed, so you'll change that. All right, let's say okay. All right, so back in loads. Now, load cases is where we define our lateral loads and our notional loads. Well, the notional loads are lateral loads, but our wind loads, our earthquake loads, our notional loads, our dynamic loads in many different places, many other cases, but that's what we're after here. So this is the key menu selection that we're concerned with, load cases. And again, load cases, these are individual load cases, not combined loads, all right? So let's define when. We'll give it the name WL. You select the type, and from the dialog box, you have all these choices. What we'll use is ASC 710. That's what we typically do. you know, this video will be too long to go through every choice, but various, yeah, various choices from user defined to wind tunnel to code requirement. So we use the code requirement. You don't do it all at the same time, so you can't switch up, whatever it's one little case defined at a time. Um, so I will define when in this case, and once you have the name, the type, and you have that setting, you click add, you receive this dialog box, or you can come up with you fill out your wind load parameters. So here it's asking us, do we want to do the X and Y directions? We do. Um, the mean roof height, is that it's going to include the parapet height, or is it just a top story, or is it user defined, something that you want? Um, use it. I like to use the top story for mean roof height. If we have a parapet, conservatively, you can include mean roof height up to the top of the parapet, right? Set this at top story though. Topographic feature, self-explanatory, apply the directionality factor, given to ASE, and it tells you whether or not you should apply that. If you use ASE load combinations, you should apply it. But this is what KD is equal to 0.85. In some jurisdictions, South Florida, for example, in Miami, you have certain building departments. In specific, I'm going to say, I believe it's Coral Gables, where, well, in Miami, not just Coral Gables, but I was working on a project in Miami where we were asked not to use this factor as 0.85, but to use 0.1, which obviously increases your wind loads, and it's conservative. But when you use ASC load combinations, you want to do this, but the directionality factor get into it accounts for the direction of the wind, and when it's coming square on, it might be considered as 1.0 and not reduced. Basic wind speed, whatever is the code requirement for your jurisdiction. I'm going to pretend I am in an area that has 110, so I'll use 110 for now, not fool around with this thing. But, I think the value that we use in South Florida, again, this wind speed, this is an ultimate wind speed. I think the value for ultimate wind speed in South Florida is up to like 150 or something. In hurricane zones, that's what you might use, 150. If you're in the mid-Atlantic area, Maryland, DC, and Virginia, this value is actually 115. Some jurisdictions, some building departments or agencies might use 120 for this value. This is the ultimate value. This is not your nominal wind speed, so-called ASD value, service load. This is at strength load values. So for this structure, we're going to use 115, and then we'll change it in the future. The gust factor will be determined. You can determine it based on a calculated frequency or user-defined frequency. So we'll use the calculated values for now. For the rigid structure determination, you can either assign it as a rigid structure or you can let the computer determine it. It's best to let the computer determine it. The software program does a great job of doing that. And then damping ratios for flexible. The default of 0.01 is fine. These other two boxes are self-explanatory. You can get into the help menu and find out more information on this dialog box, but for now, nothing needs to happen here. We don't even need to consider a minimum load because we're good with what we have. It's going to be above the minimum. And I'll use exposure C just for kicks. Once I say OK to that dialog box, I get 12 wind load cases generated automatically by RAM frame. Now I can go and define my earthquake case. I like to use EQ for earthquake as far as my label is concerned. capital EQ. Again, I'm going to define it based on ASCE 10 using the equivalent lateral force procedure. I'll add this, and X and Y directions. I have the opportunity to add eccentricities or none. Just for simplicity, I will use no eccentricities, and therefore I will only get two cases here. Earthquake in the X and earthquake in the Y. For my R factors, I'm just going to use 3. Say I have a seismic force system that has not specifically been designed for seismic resistance. That's applicable to steel structures only. So that's what we'll be using. The provisions here is for member force, but it can be for drift. That's a different story. When you use drift, you also cannot, or you should not, reduce the member forces, reduce the stiffness of the members, which we did when we selected the direct analysis method. I'll go back to that dialog box in a minute, but when you select to use the direct analysis box when you use that selection for your general criteria, you're reducing, by default, you're reducing your EI values by 20% and using a value of 0.8. And it's basically accounting for residual stress and the spread of inelastic behavior, if you will, and elasticity of the cross section. Seismic design category, I'm just going to pretend I'm in risk category 2. Most of my buildings are. Site class, it's great if we'll be in C. If you don't know, code requires you to use code requires you to use D. And I'm going to say for my S sub S value short-term acceleration, I'm going to use 0.055. I have to check out these values. I believe S sub S is supposed to be higher than, it's supposed to be higher than S sub 1. So my value for F sub 1 would be 143. For example, short-term acceleration at 0.2 seconds, and the short-term acceleration the response spectral acceleration at 1 second. TL is the length of the period. I'm going to use 8 for my zone. Importance factor is 1.0. Structure period, it can be calculated. So, or you can use the calculated value right here, or you can use the approximate value, the T sub A, and we'll use T sub A. Using the standard equation, the CT value, it needs to be correlated to the code. And right now, I think I have moment frame, and CT is 0.03. Let's verify that before we continue. That information is in chapter 12 of ASCE 7. So I'm going to take a wild guess and say that's somewhere about 300. Try to find this information real fast. Let's go to 160. All right, I'm in the earthquake zone. Go back to, it's in chapter 11. I believe it's in chapter 11. There we go. So this is what we're after here. Approximate period. Did I pass it? Yep. Go back to it. Read this information here. It actually might not be here. Let's see. Approximate period. It's in chapter 12. Yep, it's in chapter 12. All right. So we were after this table right here. Table 12.8-2. Since right now my structure is a moment frame, um, let's see here. I have a moment resisting frame system in which the frames resist 100% of the required seismic forces and are not enclosed or enjoined by components that are more rigid and will prevent the frames from deflecting when subjected to seismic forces. So the value that I'm supposed to use for steel moment frame is 0.082. Anything else that was like, if it was a brace frame or something, a concentrically braced frame, I would then need to use 0.03, or some other convoluted system use 0.02. So let's go ahead and provide RAM with the proper information here. And that's 0.028. Double checking. All right, good to go. Either way, that's an engineer decision. You have to be an engineer and figure that out. Again, this is approximate. You'll find out reality. Uh, some of your structures will not. This approximate equation probably is not so accurate, but it's okay. So we say okay, and then we have defined our wind loads and our earthquake loads, and lastly, I will define my dynamic load case, call it modal. Even though I've reduced the forces, I like to create. I still like to create this load case even for the strength analysis, and even though I reduced the stiffness, just so I can get a feel for the behavior of the structure at any point in time. It's not a In my mind, it's not a bad idea to understand it because it gives you a feel for how the structure might buckle, actually, in my mind, or the weakest directions for it, if you will, for vibration. So all you have to do is say, give it a label, select dynamic, and then your solutions that you prefer. I use eigen. Say okay. Add that. The number of modes that I request, I can request a lot. Doesn't matter if I use 16 or 25, but here I don't even need 10, but I'll take 10. Okay. You can get into this in greater detail as far as what's required by code, but there is a certain number of modes that need to be, well, that should be created so that you can include a certain amount of mass participation. All right. Notional loads. I'll go ahead and define the notional loads since we're using the direct analysis method, and to be consistent, we're going to use notional loads. So let's call it what it is. X and Y, these are the factors. The percentage of gravity that I'll use for this case. You can use a different number depending on the methodology that you're using. The gravity load types, these are all of the load types that will be factored. And then you have the option to generate additional load cases for analysis with tension only members. That's not our situation, so we say okay. And that's it. There are other things that we can do with this dialog box that's not applicable for our discussion right now. But again, the help menu is there to provide guidance. Okay, save the file. And with that, let's see, we'll just go through this menu. And with that, that's all that needs to be done at this particular point in time to run your analysis uh, for this direct analysis method that RAM frame uses. Again, it's going to run individual load cases. These are the load cases that will be ran with modified stiffness matrix. Select them all, run it. Okay, close the dialog box. Here, one thing to note is that I can pull up a report of the analysis, and it gives me a log of information. And if there's anything funny going on, you will know right here. Here it's providing me with a note to be aware of certain things. Again, it's self-explanatory, no need to discuss it in detail, but this is very useful. This analysis log report is very useful in terms of understanding the behavior structure. Then the model data, it can spit back to you all of the content related to the model data or the significant content. Again, story data, self-explanatory, also a great tool. All right. So the analysis has been ran. You know that from your dialog box, and you also know that because these values are now active. Okay. These icons, if you will, are now active so that you can see things like deflection. So let's check out the modal shape for the structure. All right. So this is just in general, and this is what you're going to get. You can see that you get the dialog box and it shows you a shape. You can scale it differently if you want. Apply that so that it doesn't look too distorted. I like to choose auto for these things, but the period of the structure is actually less than 1. So that means that the structure right here should be considered, I believe, rigid at this point. The first mode, that's the natural period. The second one, and also first mode oftentimes corresponds to the direction most likely to be unstable in my mind, or where buckling would occur. If the structure start to deflect and want to bend over, it's probably going to take that first mode. Oftentimes, in my experience, that's been the case. We can animate this and see how it would behave. All right. So we see that it's bending. It's saying that the weakest direction will be, in this case, bending about, I guess, the global y-axis in the direction in the x-axis. All right. We can find out why that is the case, but it is the case here. You can look at the second mode. It should be the opposite axis in this case. So hit, and you'll see that it's the opposite axis. Then the third mode, oftentimes this is some type of twisting, both X and Y. All right, that's the generics of that. You could get into it in detail in the future. Close this dialog box. You can check deflection, of course, for various load cases. This is what we have in the dead load. This is what we're getting as a worst case scenario for whatever the dead loads are for this particular beam. Telling us what we have. It's animated by 200, so I mean it's scaled up by 200, so it looks a lot worse than it actually is. Close this dialog box. So anything could happen. Actually, let's just do wind in the X. We can make sure we see what we're expected to see. These are values that correspond to the worst case deflections. I say auto here because I could say X, but auto is what I'll use. But you know, if it's deflecting in the x-axis, that's what you want to see. You can do that. So auto say apply for the x-axis. There you have it. It's animated. Take a look at it. All right. Close. Same thing can be done for the Y, and also for earthquake, wind, or any of these other load cases. All right. So once the analysis is complete, you can start investigating the structure. Various tools that, here to do that. The applied story forces, the applied building shears, story shears, the applied forces to the frames. These three buttons I always use, well, four right here actually, to see the member forces to investigate my structure in greater detail. They've helped me tremendously throughout my career, and it's extremely important that a structural engineer know how to use these buttons in particular. So graphically, I could change what I'm looking at a little bit by um, turning off the deck. I can turn off the grid. I can turn off the gravity beams or gravity columns and just focus in on my lateral frame. All right. I can actually put in some, if I wanted to see the member sizes for the columns and for the beams, I can do that using the view members show options dialog box. Could take a look at their fixities, which is pretty important in terms of why this thing is behaving any which way it ends up behaving. Reduce the size of the text a little bit. I can show some nodes, frame nodes, etc., etc. It's a lot that can be done. Okay. All right. Now let's design the members. So I get into to do that, I have to change the mode. So I could go from the mode menu and change here to standard design provisions. When I do that, the dialog pops up and tells me to select a design code. We're using ASD, as I said before. Say OK. Then another dialog pops up and tells me, hey, what code are you using for the load combinations? Well, I just chose ASD. You would think it would do it automatically, but apparently there are many options. So IBC 2015 or 18 ASD combinations, or the 9th edition, etc., etc. So there's a reason for it. Obviously, I'm just being sarcastic when I say you do it automatically, but I think like it should all be one setting. But regardless, you can get into here and select your load combinations. What's your SDS value? We have to figure that out. For now, I'm just gonna throw a number in there like 0.1, I don't know, 3. We'll change it. I'll tell you where to find this value. These are all the individual load cases that were analyzed and available. Here is asking me my redundancy factor. What's the row factor? 1.0 for my structure. Works and it's accurate. The notional loads, I can consider to combining it with all load cases or with your gravity only load cases. All load cases is the worst case scenario. I don't have to combine it with any in certain instances, or I can provide it only with gravity in certain instances. And for this structure, we'll combine it only with gravity and then validate our assumptions afterwards. And we can always modify this information if we were incorrect. So we'll generate the load cases by clicking on that button, and you see from these load cases, we generate load combinations, and that's 1 through a whopping 92 load cases here. Lots of fun. And this is without earthquake in the earthquake eccentricities included. So say okay. And then I'll just run the analysis, and these are your designs. It's telling you what works and what doesn't work. It fails, it gives you the ratio, and you have to modify it from then. We'll stop at this point. Okay, picking up where we left off in the lateral frame analysis of the structure, we've seen that we had members that were reported as failing. We have to investigate why. Whenever that happens, it's actually time to ensure that all of your analysis is correct. I mean, you're always going to do that, but when that happens, for sure, you want to go back and check all of the previous settings and make sure that you aren't conservative in some instances, or that you've modeled everything correctly. And of course, you need to investigate in order to figure that out. So one thing that we'll do is just to reset this video, so to speak, and go into where we left off. We will run the analysis again. Let's run it one more time. I think I might have canceled by mistake. Okay. Going into the steel, and we will leave everything as is. Let's go ahead and turn off all of our gravity elements. Run the code check. And this is where we left off. These member sizes. Let's go ahead and turn on these member sizes. We'll turn on the size and the fixities, because that's all of the important information. All right. So immediately we can see that we have moment frames, but we didn't actually provide the right fixities there. This member is failing. We'll still investigate why. I mean, we want the beam and the moment. I mean, beam and the column to be connected with the moment connection. That may not be our problem. In fact, I know it isn't. But what the real problem is we'll go into here and we'll see K over R was exceeded for the weak axis. Why? Of course, that'll be the same thing over here, because this structure is completely symmetric. Point is, you can go into the member analyses and figure out what's going on. Now, I'm getting this member right here being stressed out to essentially half its capacity. And of course, the reason why this is going on for sure, even though it's working, the reason why it's going on is because of the boundary conditions. So first thing first, let's update our boundary conditions. We do that by going to the assign menu, and actually I think we need to be in our analysis case so that we can get our fixities. Here we'll fix the left and the right, major axis, minor axis, torsion, everything for all these beams. So say okay, all at once. All right. So just for kicks, we'll run the analysis again, and without changing anything else, we'll take a look at the effect that my previous changes has on the structure. All right. Go into steel. Okay. Leave everything as is. Go ahead and do a code check. This number should go down. It did dramatically to 0.26. Nice. Hey, this thing is upside down. I agree. It's about a rotation. The RAM, as you face it, it rotates up or down. That's interesting. Nonetheless, these two members are still failing as we would expect because changing the fixities does not change the KL over R value. So it's just still telling me, hey, KL over R is not looking good, even though it has a different so-called K here. But because this is direct analysis method, K is equal to 1, so that doesn't even register. So L over R is greater than 200. Uh, that particular ratio goes into uh, handling, really, for compression members. So it's not as if this is an issue per se, but it's just something that has been given to us by really rule of thumb. It's not an actual, it may not be an actual strength issue. All right. But it's something that you do not want for columns, and I certainly don't design it for columns or any compression members for that matter. And make sure that it's braced, and we don't want to. I mean, it's going to buckle about the weak axis. Last thing we're going to do is help it, right? So close that. We don't want to help it buckle about the weak axis by not putting anything there. So we're going to make sure that that's braced as a compression member. All right. So with that said, let's save the analysis. So that's one of the issues. Let's go ahead and update that one issue first, just to prove that it's that K over R that's causing that beam to fail according to this analysis. We'll do that by adding a brace to it um, at its midspan. So save and do a data check. Okay for this phase, if you will. It's okay. My modules all go red. That has not been completed. Let's go ahead and complete those gravity designs first. Take a look at the sizes. Everything's okay. Take a look at stress ratios. We can show values, as we said before. So let's close this out. Obviously, nothing is shown for our gravity members because we have to be in RAM frame to see those stress ratios. Lateral forces are not included in this analysis. We'll do the same for RAM column. Analyze and design, show some values for gravity, spinning around. Nothing looks crazy. Of course, you can tell that by the color just as well. All good there. Exit out. Get back into RAM frame. We'll run the analysis again. We didn't do anything special other than add a brace. Okay, close it. Draw still. So, okay. Go ahead and turn these things off right away. Do a code check. All good. All right. So that's the formal process of analyzing, designing, reviewing, reanalyzing, and designing. Now, again, like I said, we have. I will make sure that we're doing everything right. This is about the proper settings just as well. So I know that there were some placeholders that were incorporated earlier for my seismic load case. So I will go ahead and update those placeholders. However, before I do that, I am going to take a second to go into the calculation of the self weight that would actually be tributary to the diaphragm. So here, under criteria and self weight, if you want to include all of the mass in your structure, columns and walls above and below, you would select this analysis. You would select this section rather to include the analysis. If you want to do it half above and half below, which is recommended by many individuals for, if not all, for your frames, that's what you should do. It's deemed to be appropriate. The theory behind it is that for the frames, the lateral forces that are halfway between the first story and the ground are transferred directly to the ground, so no stress is seen or no forces are seen from the structure, from the lateral frame resisting system in particular, um, from the first half of your story, if you will, or even the basement. So that's assumed to move with the ground, and therefore there are no earthquake forces generated. You can go to various websites and investigate that a lot more. I did it, and I came to the realization that it's not a bad idea. But worst case scenario, you can include the full mass above and below if that makes you uncomfortable. That's for the lateral frame resisting system. Some people may view it differently for the foundation itself, especially if your foundation is on piles. You probably want to make sure you include all of your forces, all of your mass from above, if it's on piles. And I would say even more specifically, if you have the first layer into the ground of the piles, if you will, from the ground to the point of fixity. If that's soft soils or liquefiable soils or anything like that, you're in a whole different ballgame, and you should include all of the mass, right? And in order to make sure your structure is stable. And you may want to include your foundation in the analysis in that instance too, to include the P delta effects from the sway of the foundation just as well. All right. So anyway, we will modify this to half up, half of the columns above and half of the columns below included. Say okay. I get that warning. Once again, I'll go back real quick just to make sure that we see what this thing was telling us. Uh, Hopefully it actually happened. It pops up, but it basically was telling me it has to redesign. Okay, so that was our one shot since we changed it then. Oh, since we had to redesign, we will redesign here, gravity and lateral. Complete. Take a quick look. No, this is not necessary, but I just do that just for kicks. Gravity, we're all good there. Exit. Go into my lateral frame analysis. Now to see the effects of the change, go into my loads menu, go to gravity loads, and I see I have 294.31 kips of dead load. Okay, and according to the diaphragm. So they say, and the live load, right? That's the total load. That's the total gravity load from the structure. I've double checked that several times with this one story, and it's exactly that number. Checked it by hand and checked it using another computer, and it's exactly that number. Why they put it at the diaphragm level um, needs to be discussed with RAM, but that's the total gravity. However, if you take a look at the mass, you'll see I have less. I have 283.49 for my weight. So let's see, the gravity load is 294, and this dead load only, so to speak, weight is essentially 284. Well, that difference in 10 kips is half of the weight of the column being tributary to the ground. But this is actually what's going to be used in our calculation for earthquake self-weight, effective weight of the earthquake based on the loads we've inputted so far. Say okay, save that. I mean, I didn't do anything, but we'll save it just for kicks. Again, like I said, let's go ahead and update our placeholders that we had here for our earthquake. Those placeholders are S sub S values and S sub 1 values. Oh, I've already changed it. All right, so previously this was some other number. You can go back to the video and view it, but it was a smaller number than that. And S sub 1 was a larger number than this. Essentially, it was vice versa. So these are the correct values. Say okay to that. All right. Nothing else needs to change here. Select all. Run the load case. Okay. Let's investigate our SDS value. So this report gives us all the load and applied forces. When these are lateral applied forces and load derivations. So we have it for wind. In this case, the load case appears here. All the generic design settings are there, and then the results are shown below it. And we'll go to earthquake case, and here our SDS value is 0.143. So that's the value we'll be using in our load combinations. Also seismic design category B. This is very consistent with the Mid-Atlantic region. Save. For those that don't know, I consider Mid-Atlantic to be Maryland, DC, Virginia, and some parts of, I guess, North Carolina. But Maryland, DC, and Virginia is what we're talking about here. So save. All right, with that, one thing I want to point out is that we can investigate our analysis log. Now notice that I said that the gravity load was 294 kips or so, right? When you take a look at this result, right, this is a summary of equilibrium checks on the model. It basically provides you the reactions for each one of the load cases in your model. Here, this is germane to the lateral forces. So it's germane, rather the lateral members. So if all of your members were lateral or modeled to be lateral member, R sub Z here for our dead load case will come up to the value for all of your dead loads. But here I have 1.356 times 10 to the 2, which is 135.6 kips, which is obviously less than our 294. Well, again, this is for the lateral frame only. All right. Our same thing with our live load. Again, it's just going to give me the numbers on the lateral frame only, and it's only calculating 96 kips on the lateral frames. So that's something to be aware of. This analysis log is really the analysis log of this module, and that means the elements that are created in this module as lateral frame analysis. Other things you'll see here is the wind load in the X or wind load in the Y. All right, earthquake loads down here, 15 and 16, they should be the same, right? So 15 and 16, as far as X is Y concerned, right? I have 13.5 kips, and this is 13.5 kips. So very consistent. All right, let's exit out of that. More on that in the future. Let's investigate stability coefficients, so to speak. This is from ASCE 710, chapter 12, section 12.8.7, and we'll investigate the stability coefficients. We could get into this in greater detail through RAM, but it's essentially letting you know whether or not P delta effects even had to be included in your analysis, and if they were included in the analysis, instead of using theta X or theta Y to investigate your stability, you can use this ratio right here, theta X over the sum of 1 plus theta in X and Y, to investigate your P delta uh, effect, so to speak. And this is the maximum effect that's allowed per code. We're far under it, and in fact, we're so far under it, to be honest with you. It could be said that P delta doesn't even need to be included in this analysis, or in this structure. But when you're using the direct analysis method, you always have to include P delta effects. P capital delta and P small delta effects should be included, or taken into consideration, should we say. But I believe in direct analysis, you always have to include P capital delta. That's why you're able to reduce, or that's why you're able to use 1 for K and get rid of the effective plane effects and stability analysis of the structure. So that's what this report is about. It's very informative. You should read into it in greater detail. Just showing it to you, just to let you know, as an engineer, you need to know about it. All right. The other reports we'll go into at another time for our reports video. So coming into here, let's go ahead and check the behavior of our structure. Now we've done everything correctly. All right. We've updated our lateral loads by updating our correct earthquake parameters. We've braced compression members. We've also included the correct mass. We've done everything according to code right here. So if you have a problem now, you need to take a good look at it. And also we've updated our boundary conditions to what we intend to design. So we run the code analysis. Here we're all good. We were all good last time, but just to show you that we're all good here. This is the result. And then again, we can go into our individual columns and beams and verify the analysis, taking a detailed look at it, maybe running some hand calcs, comparing it to those hand calcs or simplified models and things of that nature. But it shows that we're good in theory, right? It seems like that, but surprise, we're not. We're not, because RAM considers only P large delta, which is deformation of the joint, in this analysis. And it does it through a modified geometric stiffness method, if you will. So it modifies the geometric stiffness by essentially creating equivalent lateral forces that are based on the dead load in the structure, or not only dead load, the axial load, and it modifies your elastic stiffness matrix. We could discuss the write-up on that at a different time, but it's a very detailed analysis, detailed review rather, But just know that it only accounts for the deformation at the joints, right? At these nodes, not in between the nodes. And it actually does it on a global level, meaning the structure as a whole, the complete matrix, not the individual matrix. So it doesn't have to iterate or anything like that. There is a discussion on that, and I'll just bring it up briefly. Say RAM structural system and if I spelled it right, it would have popped up right away. Let's see if this is the right one, but you can just do a Google search and you get into it. So here you can find out more information on it. P delta and RAM structural systems. There's even a video right here. And I spoke with the gentleman that essentially is the chief engineer for RAM, and he explained it to me via email, and it makes a lot of sense. I've looked into it, but know that it's an approximate method, right? Let's look for another page right here, P delta. This is the one that I'm actually looking for, where it's talked about its so-called geometric stiffness method, and how it's implemented in RAM is a non-iterative approach. Um, and so you can read into this discussion in greater detail. Here again, this discussion of scale factors, what to do when you're using mass or load combinations, and what are the limitations of doing this, right? So one of the things that we need to include is essentially the effects of deformation between members. And the way that we do that in RAM is by applying B1 factors. See? Now, if I didn't do this and I ran a report, the great thing about RAM is that it actually has these validation reports, at least for ASE 360 indirect analysis. So you would run this report and it'll say, look, it's an invalid analysis because you didn't apply your B1 factors. All right. And you can read this report in greater detail. That's the great thing about RAM. It has beautiful reports, uh, very informative for the design engineer. So apply it. Let's go ahead and save it. Let's rerun. You'll notice that really not too much changed here. Okay, and let's go ahead and check our report. It's kind of like it's helping us to see whether or not we've done the right thing. So it's really dumbing it down, if you will, so to speak. And it's important. It's not dumbing it down, but it explains it in its basic terms because structural engineering is so complicated oftentimes, and there's so many parameters and different codes and uh, different materials. Those material codes have their own requirements. It's just so much going on that it's extremely important to break it down to its fundamental levels. And RAM, like I said, does a great job of doing that. So now we're all good. Um, and that's it. Let's see if there's anything else that needs to be shared at this point. I don't think so. You could code check criteria. You could go into these reports. Okay, this would be for frame level. Right now, you have to give frame numbers in order to find that information. Right now, all of my frames are numbers 0. So it would give me the results, but it would give me the results of all frames at 0, not on the individual. Well, not if I were to number these frames separately as 1, 2, 3, and 4, um, which isn't a problem or anything. This is just a way of organizing the work, just so you see what I'm talking about here for my frame numbers. turn on all the frame numbers right here. Apply. So they're all 0. Uh, let's go ahead and clear that out. All right, but we'll talk about it in greater detail. But again, you can go to code check criteria, uh, figure out, you'll see it's going to generate a good deal of data here. No, not as bad as I thought it would be. Investigate that. Get into this report at another point in time. Let's see, like I said, that completes our analysis. There's nothing else that needs to be done to the structure other than, personal, I guess, investigation of drift and things of that nature. Ensure that you're good, but you can see from our direct analysis method that the B2 factors, we know they weren't applied. The maximum B2 factor essentially is 1.07, which is pretty small. This B2 can represent your ratio of delta 2, if you will, or delta second order over delta first order. It represents the drift, so to speak, or lateral deflection. And if this is a large number, you're probably in trouble and you need to redesign the structure. The computer will also show it should wash out in the code check, but you will see that from your B2 analysis, B2 number, you're in trouble if it was large. Now, even though this report, let's go back to it, even though we're saying that it's good and everything, and you are good here, it's still incumbent on the engineer to verify what's going on for that structure in greater detail, and don't use this as a crutch and essentially say that that's all that needs to be done. You may need to investigate what's going on an individual basis. Like, for example, this frame right here, it has wind load. How is that wind load entering into the structure? Well, through the cladding. And the cladding, if it's attached to the underside of the beam or the side of the beam somehow, you're going to have some local effects if the deck is considered not to be bracing the structure, for example, and that load doesn't go directly into the diaphragm. So that's one issue. Another thing is the same thing could be happening here with the columns. It could be wind load on that's actually tributary to this columns from girts, and you need to investigate that, or any type of local bending that occurs. So what RAM frame does, as far as analysis is concerned, is it looks at everything essentially as concentrated load at nodal points, not as distributed loads or anything of that nature, and it analyzes the structure on a global level. And it's actually the right thing that needs to be done. It's enough that needs to be done. It's approximate analysis that is very reasonable and very accurate, if you will, for second order effects. And as long as your structure is stiff, you're good. But like I said, don't use the reports too much as a crutch, and investigate things on a local basis where there are variations. Other than that, we're done. Signed, sealed, and delivered. And our next video will be getting into reports or to show comparisons with other models. So that's it.